Hello everybody, welcome back to my video. In this video lecture explains you receiver noise. Noise is the general definition is noise is unwanted electromagnetic energy. Here in this case, noise is the unwanted electromagnetic energy which interferes with the actual signal and degrades the ability of the receiver to detect the wanted signal. Now, you may design a system which does not generate any noise. Case 1. Case 2. You have operated your system in a completely noise free environment. Case 2. In either cases, even though you have maintained these two conditions also, but because of the ohmic regions of the system, because of the charge carriers that are moving in the system, there is definitely a noise generated. That noise is called as thermal noise or Johnson noise. The amount of thermal noise that is generated is given by this equation KTBN, where K is Boltzmann's constant, which is equal to 1.38 into 10 to the power of minus 23 joule per degree. Bn is the receiver bandwidth. T is temperature in degrees Kelvin. This we know. Going to define Bn. Bn is integrated bandwidth. So it is given by integral minus infinity to infinity mod h of f whole square df by mod h f naught of h naught whole square, where h of f is the system response at the current operating frequency f, and h of f naught is the response at highest performance. If you plot a graph which is resulting, it may result a highest peak at some particular frequency. That frequency is this f naught. The noise figure is represented by, generally noise figure is defined as output signal to noise ratio to input signal to noise ratio. You can define noise figure in this way also. Noise figure is equal to N naught by K T naught Bn Ga, which is equal to noise out of a practical receiver N naught divided by noise out of a ideal receiver at standard temperature T naught. So this is noise figure. The same noise figure can also be defined as I have told you. Noise figure is equal to output signal to noise ratio by input signal to noise ratio. It is a measure of degradation of signal to noise ratio as the signal passes through the receiver. As the signal passes through the receiver, it degrades. The amount of degradation is defined by noise figure. Now, if from this equation, if you write it for SI, we have already got a equation for Fn. This is Fn equation. Use this is Fn equation. Use this Fn equation, substitute it here, and write a equation for SI. Then what will you get? You will be getting SI is equal to KTBN Fn S naught by N naught. Now this SI we can call it as a minimum detectable signal S min, that is corresponding to the minimum ratio of output signal to noise ratio necessary for the detection. If read this, if the minimum detectable signal S min is the value of SI corresponding to the minimum ratio of signal to noise ratio necessary for the detection, then SI will become S min, and you write this S naught by N naught separately at its minimum, then S min is equal to KTBN Fn S naught by N naught at its minimum. Now this equation, you take it and substitute in the radar range equation, which we have already derived. R max is equal to PTGA sigma by 4 pi square S min whole power 1 by 4. In this equation, if you substitute, you take this 1 by 4 this side, it will become R max power 4, which is equal to PTGA sigma by 4 pi whole square KTBN Fn S naught by N naught at its minimum. So this is called as a modified radar range equation. This is modified radar range equation. This equation will be helpful to do many calculations and further processing in the coming topics of this chapter. So one should remember this equation, a modified radar range equation. Okay. So coming to the next topic, envelope detector and signal to noise ratio. In this envelope detector, consider an IF amplifier with a bandwidth BIF followed by a detector and video amplifier. What is the role of the detector? Role of the detector is to reject the carrier and pass the envelope of the modulated signal. So this detector stops the carrier and passes the envelope of the detector, thereby giving a chance to this amplifier to amplify the detected signal, which is further given to the A scope. For a operator to understand very clearly the bandwidth of the video amplifier and second detector must be such that it should not be too high that matches with BIF. If the bandwidth is very large, there is a tendency that noise signal will also enters into the system and degrades the quality of the output. And it should not be very less that the video signals, some part of the important video signal may cut out. So it should be moderately selected. Bandwidth of the video amplifier must be moderately selected, that it will not lose any part of the actual desired video signal, and it should not match with the actual actual BIF also. Okay, hope I understood what is the concept. If there is any doubt, please leave a comment. Thank you.